I am Avery Fiore, an SAS FRC captain. This playlist is an FRC CAD How It Was Done playlist explaining one of Team 4817's off-season projects in 2023. We decided to split up the CAD team into 3 groups and have each of them CAD a 5-axis arm. Obviously, I'll be talking about my own team's designs in these videos, and this was more a theoretical project where we CAD'd this and have not built these designs as of today. Anyways, to get into the actual project, this was our overview document that we gave all the teams, and basically the challenges we're going to make a robot that can pick up this soda can, standard soda can dimensions, and pour it into someone's mouth. And the starting size restrictions are the standard 30 by 30 inches, and while there are many different ways to actually go about this, in theory, if this was just a real challenge, the whole point was to make a 5-axis arm. Considering some of the restraints we had, we ended up actually going with a 6-axis arm in my team by adding an extra axis in terms of linear slide. But to give an overview, I guess I can show with the final CAD a bit. We have one axis for the turntable down here, which I can drive. Right, rotates all around there. And I'll dive into deeper details into each of these different mechanisms in the following videos. Right, second axis is the first arm joint. Third axis is the second arm joint. Fourth axis, which is the additional added axis that wasn't initially required, was this linear slide sorts. Fifth and sixth axis I don't have jointed up in the program, but they are sort of kind of module design here, and basically it allows this whole apparatus to turn around this bearing, and then it can actually pivot this whole section or the claw itself around this pivot. And so that gets your 2 additional axes, and then you have your claw itself. So it ended up being 6 axis, but well, we're calling 5-axis arm, just has a nicer ring to it, I suppose. So in this video, I'll be covering specifically the planning section and of my team's process. So to start on any of these things, like the best thing to do is kind of just draw it out on a Miro board. So this is a very bare bones design, but basically the idea is did some calculations, right? 30 by 30 inches. In theory, that will allow you to put this these arms diagonally across this 30 by 30 inch base and get something that's about 42 inches. Now that's assuming that your claw does not end up being very long, which, well, first personally I predicted would be possibly the case. So considering that this first length can be 21 inches, the second length in absolute maximum, assuming the claw had no length, could be 42 inches, that's actually not going to be quite long enough to just extend all the way. So that's how we knew we possibly have to add a 6th axis, either by using a linear extender or making a 3rd arm joint. We decided that a 3rd arm joint was not ideal because of the additional amount of torque you might need to potentially calculate if like the arm was fully extended. Actually, well, that doesn't really matter. It's more that it's going to be harder to motorize because of how you have to, assuming we want to keep all the weight near the turntable, so we want to position all the motors low down, the way you would have to belt or chain the system would get really complicated if you had a 3rd arm. So if you just make the 6-axis a linear slide, that ends up being better. And yeah, if you see in the file CAD, you know, this is about 5 inches. The claw ended up being way longer than that, so it was great that we had a linear slide so it could actually reach the full height required from the ground to a person's mouth to pour soda in. When drawing these Miro boards, I would suggest that you do more detail if there are more people in your team. In my case, I only have myself and Lock, and we were able to orally communicate what was going on, and we just remembered stuff, and it worked out well enough, okay, and we're, you know, had good communication throughout the entire process. But the more people you have, the more you want to lay out exactly how this design is going to look in your beginning stages of your planning. Now, something we did do together was run all the gearbox calculations. So this is kind of just a short review for people who might not remember how this works, but basically we go to A and B calc, okay, and let's say you have 20 inches for your first arm, so that's considering this is 21 inches, just 20 inches is a decent approximation. And let's say that the total weight of the entire arm could be 40 pounds, and that we're going to run these all off of Falcons. The reason why it's only 20 inches is because if you take out if you have this arm extend all the way over there with its total of about 60-inch length, and then you have like the claw all the way on the end, and then all of this weight on the turntable over here. We just estimated that'd be about 1/3 the distance would be the center of mass, and that's the distance you actually put for your radius, the center of mass. So by doing this, assuming we have one motor, we get a gear ratio, 300:1. Now we can actually play around with this a bit, and we kind of look at what our available options are in terms of gearing this thing. So if you want to gear using 20 DP gears, in this kind of really heavy system that requires a lot of torque, in theory aluminum gears are fine, but just to be on the safe side, I want to use steel gears. The largest steel gear available is a 64-tooth gear as of current from WCP. So the highest ratio you can make is an 8:1, and then let's say in the second stage where you don't even have this 8-tooth motor pinion, the highest ratio you can make is 4:1. And then with the sprocket ratio going from a 16-tooth number 25 sprocket to the turntable sprocket that we're using, that was a WCP grade T design, that's going to give you a 240:1 gear ratio. And I can just check this in the calculator and see what it actually turns out. So this is at peak efficiency, right? But if we do 240:1, we want to look at the current per motor. And this value can go as high as 40 amps legally. I've even read research that the PDH's breakers kind of act more like 60 amp breakers, but you still have that 120 amp breaker limiting the robot's current overall, and it's just not a good idea, generally speaking, to have too much current draw. So you want to make this pretty close to peak efficiency if possible, and this is nowhere near 40 amps, so I decided that this would be a fine ratio to use. Another tip is when you're trying to figure out how to combine ratios together, this can be useful in figuring out what exactly you can make this. Strange. Okay, so once you write it this way, so then you can combine the ratios together and see what your total ratio is, and yeah, that's indeed 240:1. Okay, and so going through the rest of these, it's pretty straightforward. I'll just talk over the images. So at peak efficiency for this, using 2 motors, assuming that your radius is 45 inches, which is just, now we're removing the first arm pivot, and why it's 45 inches is, let's say your entire arm is over there. Now you don't have all of this weight here, but it's kind of the same calculation as the turntable, except you're actually powering the rotation around this axis in the circle that my mouse is moving right now. Anyway, so we estimate, and you can overestimate these values so that you make sure that the thing actually works. 45 inches, 40 pounds. 250:1 ratio still doesn't draw too much amps, so that works, and I get a 250:1 ratio by using that setup there. And it's kind of similar. Thinking you just now decide that, okay, we're going to calculate this from the second pivot. This entire thing is 60 inches, and it's going to be a bit over 30 just because you have all this weight on the end of the claw, right? But let's say that your linear slide is not always extended, whatever. We can just say it's 35 inches, a bit less weight because now you're not moving as much arm, and we can still see the current draw is fine, etc., etc., etc. Very similar calculations, and when you can use a less powerful motor, you should do that. That was in the original plan. We ended up using a Neo 550. Doesn't really matter, I guess, at the end of the day. After doing all those calculations, from there, we just peer review to make sure that we both did our calculations properly, and then from there we're going to move on to actually counting this thing.